Hello, hello. So please respond in the chat. Then I will start the session for today's class. I want everyone to utilize this particular session because you haven't performed well in second mid. So please respond. Please join the chat and ask some queries regarding the syllabus or regarding some topic. Need to be it should be like interactive session. It is not like I only wanted to speak in this particular session because the classes are done. Only the revision session is left, right? So please respond. I think only one of you people are responding. I think Chessy is responding. None of you people are responding. Please respond. Then I will start the session. Everyone, please utilize this session. Shall we start, Ceci? Or shall I wait for another 1 or 2 minutes? Because it is a live session, it should be like interactive and asking question and answer session, like, right? So please respond, and then I will. I think only 9 has been joined still. Let that number increase, see. DM them as soon as possible. I think this is our syllabus. So in the first unit, we are having about the history of quantum computing, and we are dealing with the importance of mathematics in quantum, and as well as importance of physics and also biology. I think these are theoretical things, but I will explain once more. So, and another topic is nothing but introduction to quantum computing, which is the difference between bits versus qubits. That is nothing but classical versus quantum. So again, the same question comes: classical versus quantum logical operations. I think I have given the 15 differences, so that you need to write here. I think in unit one we'll finish by 1 hour or 45 minutes. It is based on you people joining. I think only 6 are there in the session still. So this is about unit one. So shall we start or should I wait for another 1 minute or 2 minutes? I think only 6 are there still. I already intimated you people why you are not serious. I don't know. So let me start the first topic. That is nothing but the history. Let them join. I think this will be the recording session, right? No issues. They will see afterwards also. So the first thing is nothing but how the transition occurred from classical to quantum physics. So this is what you need to know. Okay. So how this journey has started. Okay. So in the classical era, that is, I'm talking about 1600s to 1800s. So since uh, from past we are only having Newton's laws of motion and Maxwell's electromagnetic theory. So that is nothing but everything seemed predictable in classical. For example, if I throw a ball, I can exactly know where the ball will land. So that is nothing but we call it as prediction or predictable behavior. So and these particular quantum revolution has started from the year 1900s. Okay, so scientists started discovering the tiny particles, such as already you know what are the tiny particles like electrons and photons. Okay, so the thing is they didn't follow classical rules, which is nothing but they are not predictable. They are completely probabilistic. Okay. Whereas in 1900, Max Planck introduced the idea of energy quanta. That is nothing but energy comes in steps. That is, we call it as quantization. Right. So in 1905, Albert Einstein explained the photoelectric effect. So that is nothing but light behaves like waves as well as particles. So in 1913, Niels Bohr described electrons moving in fixed energy levels around atoms. So if it is moving one step forward, then it will gain energy. So I think by 1995 to 1927, Heisenberg and Schrodinger built the full quantum theory. So they have stated that quantum is not deterministic, quantum is probabilistic. So if you look here, classical physics works for large objects. So large objects are nothing but cars, planets, etc. etc. So whereas quantum physics explains the behavior of tiny particles like electrons and photons or atoms. So which are tiny particles, right? So if you look here, classical world will be giving certain outcomes, whereas quantum world will give only the probabilities. That you need to remember. This is the main point. That is the main differences that you need to highlight in your exam paper. So energy is classical. In classical world, it's continuous. Okay, but whereas in quantum world, it is quantized. Quantized is nothing but at discrete steps will gain energy. Whereas in classical, the energy will be continuous. Right? So if you look here, the energy will be continuous in this particular diagram. But if you look here, the energy is step by step. At this particular point, the energy will be low. And at this particular point, the energy will be increased. So the energy comes in steps. If you look into this particular picture, this completely demonstrates simple way of how quantum will gain energy, right? So in classical world, the energy is continuous, whereas in quantum world, the energy will be quantized. That is nothing but the energy will be gained in steps, not continuously, right? So I think some are some differences I have given in this particular table. So I already mentioned it is for large scale objects like planets, etc., etc. So, but whereas quantum deals with atomic and subatomic particles such as photons, electrons, right? So the nature is deterministic. That is nothing but the future is fixed. For example, if I throw a ball, I can say where that particular ball will land. That is nothing but the future is already fixed. But whereas in quantum physics, the future is completely probabilistic. I can't say whether that ball will land there or not. I can't say in this particular room there is atoms and photons I can see. Right? So this is completely I can say just okay, I can imagine that there is photon in this room or I can imagine that there is atoms in this room. That is nothing but just a probability, right? So and the energy is continuous. Whereas here quantized, that is nothing but steps. So observation, this is the term you need to remember. So, for example, if I hit a ball, let's think, if I hit a ball that will land in a in particular area, right? So that is nothing but if I watch or 100 people watch or 1000 people watch in cricket stadium, the ball will not change its direction because of someone is watching. But whereas here in quantum, it affects the result. Okay. Already we discussed quantum or qubits behave like two states at a time. That is nothing but superposition. So if someone is observing that superposition state, then it will automatically collapse. That is what observation effect do in quantum. So if someone is observing our wave function, which is in superposition, then the wave function will be collapsed. Okay. And whereas classical physics, I already mentioned this point, classical physics obeys or follows Newton laws, whereas quantum physics completely follows wave mechanics. Okay. I think this is not required. So why quantum physics matters? So it helps us to understand how atoms and light behave. Okay. So it forms the base for quantum computers, quantum communication, and as well as quantum sensors. So the quantum theory leads to modern tech like lasers, LEDs, and MRI. Even in a medical field or even in every field, the quantum will be the leading subject in future. Okay, this is about the transition of classical to quantum. Why we require? I think you got some idea, right? Still only seven are there. I don't know why you people are these careless. So please let me know in the comment section. Is that clear? This transition from classical to quantum. If any question comes regarding the importance of biology or regarding the importance of anything, you try to write the transition from classical to quantum and then try to mention the importance of mathematics, biology, or physics, etc. etc. Okay. First, you need to write about the transition, how this transition has been occurred. Okay. Is that clear for everyone? Let me know in the comment section. Shall we move forward, Sasi? If yes, let me know in the comment section. Okay. So moving on to the first topic in our syllabus, that is nothing but role of mathematics in quantum computing. Okay. Better before moving. Okay. Let me go through this. So why we require mathematics for quantum computing? That is what the question you need to raise. Okay. So quantum computing uses a lot of linear algebra, matrices, etc., etc. That is what I said, right? Quantum gates. Okay. Complex numbers. I think you are familiar, right? I think some in some algorithms, etc., etc., everywhere you see this particular number I, that is nothing but complex number, and probabilities, because every aspect of quantum computing we deal with probabilities. Okay. Now quantum states are stored as vectors. So already you know ket0 is nothing but what is the column vector for ket0? 1 0, right? And what is the column vector for ket1? 0 1. So these all are stored in vector form. So, and quantum gates are stored in matrices. I will explain about quantum gates. Then you come to know, after these particular topic, I will explain quantum gates and classical gates. And then then you come to know about some mathematics. Okay, how it is important to quantum. For example, here is one example. So a classical bit can be either 0 or 1, but a quantum bit can be combination of both. So combination of both is nothing but what we call it is superposition, right? So a qubit which is in two states is represented as this particular equation. These also you are not able to write in the exam. I don't know why. Ket psi. What is this? Ket psi is equal to alpha ket 0. Let's take alpha here for your better understanding. Alpha ket 0 and beta ket 1. So and alpha and beta are nothing but complex numbers, not numbers, complex numbers. So where it's ket0 and ket1 are nothing but the column vectors, which is represented in 2D. So for example, I have given one example here. So we are having Hadamard gate, already I have discussed. Hadamard gate is represented by H. Okay. So this is the mathematical representation of Hadamard gate, 1 by root 2, 1, 1, 1 minus 1. So when you try to apply Hadamard gate on ket0, so try to solve this, okay, in on pen and paper. It will make you practice. Some are written very worst. Okay, this is not at all acceptable. So if you try to do the matrix multiplication, then you will be end up getting this result, right? 1 by root 2, 1, 1. So this 1 can be written as 1 0 0 1, right? So 1 0 is nothing but ket 0. 0 1 is nothing but ket 1. From there this equation has came. So you don't think after this equation, don't be confused. So how this equation has been arrived? So this is the formation. So we are writing 1 1 as 1 0 plus 0 1. So 1 0 is nothing but ket 0, 0 1 is nothing but ket 1. So this is nothing but superposition. So why I called it as superposition? Now the main question comes. So 1 by root 2, 1 by root 2 ket 0, 1 by root 2 ket 0, okay, plus 1 by root 2 ket 1. Sorry, ket 1. So if I want the probability of ket 0, then that is nothing but mod 1 by root 2 whole square, right? Mod 1 by root 2 whole square. So if you check the probability, then you will be getting 50% chance for ket 0, 50% chance for ket 0. If you also check the probability of ket 1, again 1 by root 2 mod whole square, then for ket 1 also there is 50% chance. So equal mix, that is nothing but two states at a time. That is why we call it as superposition. I think this is clear, right? So that is nothing but we'll be using linear algebra in this particular example. Now moving on to the complex numbers. So complex numbers plays a important role in quantum computing. So how? So without complex numbers, we can't create superposition, interference, and phase, right? So complex numbers, you already know I is equal to root minus I. For example, this is how your complex numbers looks like. 3 plus 4i. One is imaginary part, another one is real part. I think that is clear, right? So I have given one example here. We have representing a qubit, ket psi is equal to alpha ket 0 plus beta ket 1. I have given AB, so better don't be confused. So think it as alpha ket 0 plus beta ket 1. So where alpha and beta are nothing but the complex numbers. So if you look in this particular example, ket psi is equal to 1 by root 2 ket 0 plus I by root 2 ket 1. So where A is nothing but which we call it as alpha. Alpha is equal to 1 by root 2. Beta is equal to 1 by root 2. So if we know, if so qubit need complex numbers to store the probability amplitude and the phase information. That is what the role of complex numbers. Okay. Now moving on to the probability. What is probability amplitude? So every quantum state has amplitude, that is nothing but complex number. So if you look here, if this is my quantum state, okay, or this is some complex number, then the amplitude or the probability is written as 0.6 whole square plus 0.8 whole square, that is nothing but 1. Then if it is 1, then we say it as valid qubit. So better you go with this particular example, 1 by root 2 ket 0, that is nothing but I am not able to write here. So better 1 by root 2 ket 0, you go with that example. 1 by root 2 ket 0 plus 1 by root 2 ket 1. So I am not writing here. So better you fill it 1 by root 2 ket 0 plus 1 by root 2 ket 1. If I want to find the probability of ket 0, mod 1 by root 2 whole square. If I want to find the probability of ket 1, mod 1 by 2 root 2 whole square. That is what you need to get. And if you add those two probabilities, 1 by 2 plus 1 by 2, that is nothing but 1, right? Yes or no? So that is nothing but the qubit is valid. So, so this is the formula I think I have given here. So probability is nothing but amplitude whole square. Okay. If it is like for this example 0.64 plus 0.36, it is valid, right? So mod, this is nothing but mod. It should be mod, right? Not just square. Mod alpha square plus mod beta square should be 1. Okay. I think you please solve this example and let me know the answers in the comment section. I want you to solve this example. Ket psi is equal to root 3 by 2 ket 0 plus root 1 by 2 ket 1. Can you please solve? And I want everyone to answer in the comment section. What is the I want the probability of ket 0 and the probability of ket 1. I want the probability of ket 0 and the probability of ket 1. Please be interactive. So you need to know the basics first. So can you please solve and make it fast? Answer in the comment section and then I will proceed for the next topic. What is the probability for ket 0 and what is the probability for ket 1? That is what my question is. Very simple answer. So make it fast. Probabilities is a separate topic for you people. If any question comes, you need to solve it. So what will be the probability? That is what I am asking. Please respond. 3 by 4 for ket 0, 3 by 4 for ket 0, okay. Next 4 for ket 1. Okay, thank you. Nice. So please be interactive. So that is nothing but we just done the mod, right? So if you do the mod square, then you will be getting 3 by 4. If you do again same way, if you do the mod square, then you will be getting 1 by 4, right? So if you add them, you'll be getting 1. So that is what you need to check if any question comes. Now moving on to the most important topic. This is there in the second unit also. I won't cover again separately. So please listen. Hilbert space. So Hilbert space is nothing like, for example, if you are staying in the room, okay, that room is nothing but Hilbert space where you exist. Okay, same way, for every quantum state, for every qubits, everything, the Hilbert space is like a home. Just think, it is very easy. Okay, so every quantum state qubit, okay, is like point inside the room. For example, if you are staying in the room, that is nothing but that is represented as a point. Okay, so more qubits, for example, only two people are staying in a room. Small room is enough. If 100 people want to stay in the room where two people stay, it is not possible, right? So as the qubits, as the number of states of the qubits increasing, the Hilbert space is increasing from 2D to 3D, 3D to 4D, etc., etc. Okay, so for example, for one qubit there is only two basis states, so that is why we require 2D. Okay. If it is for 2 qubits, there will be 4 possible states, right? And then we require 4D Hilbert space. For 3 qubits, we require 2 power 3 qubits or 2 power 3 basis states. That is nothing but we require 8D Hilbert space. For n qubits, it is growing exponentially. That is why we require 2 power n Hilbert space. Okay. 2 power n d Hilbert space, right? Is that clear? I think I have given one example. Uh, for example, here is my quantum system, and this is represented as two vectors. Okay. So, for example, I am talking about two qubit system, not two qubit system, one qubit system. So, it is represented as C1, C2. So, qubit system is spanned between C1 and C2. I think this is what I mentioned in the class notes. Don't be confused. I haven't included in this particular slide, but please try to write down that in your examination. Is that clear? Hilbert space, mathematics. If any doubt, let me know in the comment section. So how this is done is nothing but, see, in the quantum system is between C1 and C2. How we denote, how we represent is nothing but, so we say a quantum system is spanned by two vectors C1 and C2. That is how we represent. Okay. If it is clear, let me know in the comment section and ask others to join, because it is not a forced section, it is a revision session, right? For you people, I am investing this time. Shall we proceed for next topic? If yes, please comment yes. Please respond. Until you respond, I won't move forward. Thank you. Thank you, Srikant. Nice. Some are very interested, keen. Is there any doubt in this particular topic regarding importance of mathematics in quantum computing? Srikant, is there any doubt regarding this importance of mathematics? So I think I have covered complex numbers, probabilities, linear algebra. Linear algebra is nothing but matrix representation for quantum gates, right? Complex numbers will be using in all the algorithms, right? And even probabilities we need to calculate, right? Thank you for your confirmation. Still, is there any doubt for others? Please let me know. Don't think, don't be panic. Okay, it is think it of like interactive session. If there any doubts, please let me know in the comment section. Please post it. I will clear all the doubts. What kind of probability? What kind of probability will be asked for this? So that is nothing but you will be given for as per my knowledge. I don't know how they prepare the question paper for semester. So as per my knowledge, they may give one quantum state in this format, and they may ask you to find the probability. I think in the mid one, you people solve one example, right? I think also I have also explained in the class notes. So go through that example. They may give some quantum state. It may be like this example or some other example they may give, and they may ask the probability, find the probability of get zero or find the probability of get one. Only this question may come from this particular topic. Other than this, I don't know. If any question comes, they may ask what define the importance of probability in quantum computing. So you need to write all those things. Okay, is that clear? Is that clear? Let me know, please. Please be interactive. Thank you. Thank you for the confirmation. So before moving on to the importance of physics, etc., etc., I think I need to go with syllabus, right? Okay. So after the importance of mathematics, I will proceed the next topic, the importance of physics. So you people already know. So physics, if any question comes regarding importance of physics, please dump all this matter. So if you look in this particular exam, in this particular PPT, I have given the fundamental principles of physics. So make quantum mechanics. So that these in this quantum mechanics is nothing but these are all the fundamentals of physics. Okay. So you need to mention about superposition, entanglement, uncertainty principle, wave particle duality. If any question comes regarding importance of physics, you please dump all these four topics, and even you can also write about quantization. So in quantization, the energy comes in steps, not discrete, not continuous, sorry. The electron gains energy in steps, not continuous. So that is what about quantization. Please mention that also. So now moving on to the concept of superposition. So this is the basic principle of physics. Okay. This is the definition. A quantum particle can be in several states at a time or two states at a time. That we call it as superposition. For example, let me give you one example. If I toss a coin, I'll be having only two outcomes. Either it may be tails or heads, right? But if it is spinning in the air, okay, let's think of it, the coin is still spinning in the air. Then I can't define whether the coin is head or tail, right? So that is nothing but two states at a time. That we call it as superposition in terms of quantum. Okay. And you please mention these particular equation everywhere. Okay. Ket psi is equal to, what is this? Ket psi is equal to alpha ket 0 plus beta ket 1. This is single qubit system. If it is two qubit system, ket 0 0, ket 1 1, ket 1 0, ket 0 1 will be there. I am talking about single qubit system. So where alpha and beta are nothing but probability amplitudes, and it should satisfy these condition. Mod alpha square plus mod beta square should be equal to 1. Okay, that is what the condition for a valid qubit state. So simple example, already we have solved this example. Let's start Hadamard gate with, let's start a qubit with ket 0, and then we'll be applying Hadamard gate. If you apply Hadamard gate on ket 0, you'll be end up getting this result, right? So that is nothing but 50% chance for ket 0, 50% chance for ket 1. So after measurement, the wave function collapsed to single state. This you need to remember. So if you measure it as ket 0, it will collapse to ket 0. If you measure it as ket 1, it will collapse to ket 1. If you measure it as ket 0, for example, then the ket 1 information will be gone. It will be only having only the information of ket 0. If you measure it as ket 1, then you will be losing the information about ket 0. That is what you need to remember. That is what happens when you measure it. That is why I have given here, it will collapse to a single state. That is nothing but classical state. Classical output will be only either 0 or 1, right? So same way, after measuring the qubit system, you will be having only classical output, either some 0 or 1. Okay. Now, moving on to another concept, entanglement. So what is entanglement? So entanglement is nothing but two qubit state share a combined state. Let me give you one example. So if I'm having two particles, just think I'm having two particles and the two particles are entangled. Okay. If I change one particle, another one reflects. Okay. For example, if you gone through some movie called Twin Brother, in that particular movie, if you affect one twin, other will instantly know what is happening, right? Even they are far apart. Same way this entanglement phenomena works. Even if your two particles are entangled, if you are far away also, you can know what is happening here. Okay. Changing one qubit instantly affects the other. That is what about entanglement. So the simplest entangled state is written as, so this is one equation of Bell state equation. This is okay. Ket psi plus. This is positive Bell state equation, which we call it as maximally entangled particles. So what this equation says is nothing but, I am talking about two qubit system. That is why I have given two probabilities here, 0 0 and 1 1. What if I measure the first qubit as 0 of first particle, then I can exactly know, instantly know the second qubit will be also 0. If I measure the first qubit as 1, the second particle which is entangled with particle 1 will be also 1. That is what this equation says. Okay. Now let us go through one simple circuit. So initially, every qubit will be started with ket 0 and ket 0. Okay. Initially, two Q1, Q0 and Q1 will be started with ket 0 and ket 0. So after ket 0, if you look, we are applying Hadamard gate. For Q1, there is nothing. Until here, there is nothing. Okay. So, but here, there is Hadamard gate. You know, H of ket 0 will be, what it will be? H of ket 0 will be 1 by root 2 ket 0 plus 1 by root 2 ket 1. So that is what I have written here. If you apply Hadamard gate, you will be getting 1 by root 2 ket 0 plus 1 by root 2 ket 1, and down qubit will no operation, right? So if you do the tensor product, you already know, right? Tensor product ket 0 0. Tensor product of ket 0 ket 0. What will be? Combinedly, we should write ket 0, 0. If it is ket 0, ket 1, if it is ket 0, ket 1, please let me know in the comment section. Ket 0, tensor product with ket 1. Please solve. Everyone, everyone please answer me. I want the tensor product of ket 0, ket 1. Please let me know the answer. Ket 0, ket 1. Tensor product with ket 0 and ket 1. I will proceed when you answer, when you people answer. Until then, I will stop. So please be interactive. Try to understand the concepts. Don't skip this particular session because it is useless if you skip. Same as your classes. Okay. So what is the tensor product of ket 0, ket 1? Please answer me in the comment section. Ket 0 tensor product with ket 1. Right, ket 0, 1. Why you are marking it as question mark again? The answer is correct. Ket 0 tensor product with ket 1. That is nothing but combinedly we need to write it. Ket 0, 1. Right. You are right. What's your name? I am not able to see the proper name. I think you have joined with another mail. Ket 0, 1 will be the answer. Okay. That is correct. And now if you look in this particular example, if you do the tensor product again here it will be like 0, 0 because down qubit we haven't operated anything, right? So ket 0 remains unchanged, but the top qubit becomes this equation. Now you try to apply ket 0 with the bottom qubit. If you do the tensor product, ket 0, ket 0, ket 0, 0 and ket 1, ket 0, ket 1, 0. Now we need to apply C naught gate. So already you know, if this is control, this dot symbol represents control and this plus symbol represents target. I think should I again explain this C naught gate? No, right? I think you guys are familiar. So this dot symbol represents ket 0 and this plus symbol represents ket 1. So what does this C naught do? If the control is if the control is the first qubit, okay, in this particular exam, the control is at first qubit and the target is a second qubit, right? If control is 0, for example, I am taking one state 0, 0. The control is at first qubit. So the control is here in this particular example. This won't change. This will be written as it is 0, 0, right? So if the control is, for example, here, if you take it 1, 0, here comes, if you apply C naught on this particular equation, you'll be ended up getting 1, 1. Because if the control is 1, the target will be flipped. The target here is 0. The target is flipping, right? That is what I have written here. So if the control is 0, for example, here I will explain better. The control is 0 in this particular example. This is the control in this scenario and this is the control in this scenario. If the control is 0, it won't change. It is written as it is. If the control is 1 and the target is changed, target is flipped, right? Now moving on to, I think this is clear, right? Now moving on to another important topic in physics, uncertainty principle. So which is proposed by Werner Heisenberg's, okay? So it is also called Heisenberg uncertainty principle. So it states that it is nothing but we can't exactly define the position and momentum of a particle. Okay. So that is what I have given. States that position and moment cannot both be known exactly. For example, if the fan is rotating, I can't know the position and momentum of that fan, right? So the relationship is given as delta x into delta p, okay, less than greater than or equal to h by 4 pi. So where h is nothing but Planck's constant, delta x is nothing but change in position, momentum, sorry, delta p is nothing but change in position. Okay. So this is what about uncertainty principle. And moving on to another thing is nothing but wave particle duality. So name itself has the answer, wave particle duality, dual role. Okay. So if you see light and matter behave as both waves and particles. So it will travel both as waves as well as particles. So which is demonstrated using the double slit experiment. So what is double slit experiment? Now comes the question. So for example, I am having some source of light or some photon, let's say. One wall is there and I have made two slits. This is slit one and this is second slit. And I am making it to travel to through these two slits. I'm making this light source to travel to two slits, and I am having a screen here, some black screen here. Okay. So if no one is observing, they are traveling to two slits, and they will form interference pattern inside the screen. So this is how interference pattern will look like. So the this pattern we call it as interference pattern. Interference definition, you simply write it as two or more waves collide each other and travel. So that is what happens if you make two slits and make this photon source or some source to travel inside the screen. This is how quantum behaves. So quantum always behaves or travel in interference pattern. Quantum particles always travel in interference pattern or create interference pattern. So until this interference touches the screen, it will travel in this particular pattern. Okay. I think this is clear. For example, if someone is observed, just think about one scenario. If if someone is observed here, if someone is observed, then the particle will travel like this, dot, dot, and it will hit here. So you won't see the interference pattern until someone sees it. It will be in interference pattern. If someone watches it, it will collapse. That is what happens. The observation or measurement or observation or measurement, everything, it will collapse the wave function. That is what you need to remember. So the wavelength of particle is given by lambda is equal to h by p, where h is nothing but Planck's constant. Okay. This is about wave particle duality. I think this is this clear? This is about the physics. Is that clear? Let me know in the comment section. If you are having any doubt, let me know, please. Only two are responding. What happened to CR also? CR is also not responding. Arjun responded at the start of this class, but still no response. Sai Charan also. Only Srikanth and Jaya is responding. Please respond in the comment section. Then I will move forward to another topic. If that is clear, if you're having any doubt, let me know now itself. And again, I'm again saying these are the same topics that are there repeated again in unit 2. So if you come across these topics perfectly, then it will be a bonus offer for you people. You can write both in 2 units. If yes, please let me know in the comment section. If you are having any doubt, let me know now itself. Someone please respond. Are there anyone? I think it's time to stop. Sissy, make sure everyone please ask them to join because it's almost 1 hour session, but still no one is there in session. Okay, let me proceed to the next topic before going on to. So let me boost up you regarding quant. So from first unit, any problems? So there will be no problems as per my side. I can suggest you nothing but. So they may ask you some questions like importance of mathematics, physics, and biology. This may be the first question, and then you try to write about the transition of from classical to quantum. You try to mention all the years that I have mentioned in this PPT. I will share after this particular session. And one more question may come like, what is quantum computing? And can you differentiate between bits and qubits? Okay. And one more question may come like classical versus quantum. Again, the same answer. What once you learn one answer regarding classical versus quantum, then you try to mention it in every answer, no issues. Because the same answer, the same points will be repeated. Even here also, bits are nothing but what bits are represented using binary digits 0 and 1, right? But whereas qubits, it is represented as ket 0, ket 1, or superposition, or both we call it as. Okay. That is what the you need to write in this particular scenario. You try to mention ket psi is equal to alpha ket 0 plus beta ket 1, where alpha and beta are probability amplitudes. Okay, all those things you need to mention in bits versus qubits. Okay, whereas bits only work serially. It is not at a time, right? Only one possibility at a time. Whereas here, n possibilities at a time, which is nothing but 2 power n possibilities in qubits in quantum. That is what you need to write in this particular scenario. I think no problematic in this unit from this unit 1. The problem comes from but unit 3, unit 4. Okay. I think rest 3 units are completely theoretical. Okay. So before going on to some, thank you for the confirmation, Srikanth. So let me boost up with some with easy uh, uh, way to understand quantum. So better we'll start with basics. So you'll be having some logical gates. You try to write. I think this is there in unit 3, unit 4. So I'm covering this topic here itself. before going on to another topics, you need to know about these gates. So you already know I'm talking about classical gates. So not gate. So which is nothing but if input is 0, output is 1. If input is 1, output is 0. That is nothing but it is quite opposite to the input. Okay. That is about not gate. I'll quick recap this. I think I don't invest much time in this particular PPT. So and then the thing is nothing but AND gate. So if output is 1, only when both inputs are 1. So if you look in this particular scenario 0 0, the output is 0. 0 1, 0 again. Okay. 1 0, again 0. If it is 1 1, the output is 1. That is what about AND gate. Now moving on to OR gate. Output is 1 if only one input is 1. Any one of the input is 1. For example, 0 0, no, nothing. So that the answer will be 0 0. 0. 0 1, the answer will be 1 because one of this output, one of this input is 1. In the same way, in the third scenario also, the one of the input is 1. That is why the result is 1. In the fourth scenario, the two inputs are 1. The answer is 1. Okay. Now moving on to another gate, NAND gate. So if you look NAND gate, output is 0 only when both inputs are 1. Okay. Output is 0 only when both inputs are 1. Only these particular scenario, the output will be 0. Rest of all the cases, the output is 1. This is about NAND gate. And moving on to NOR gate. So if you look the NOR gate, output is 1 only when both inputs are 0. If the both inputs are 0, in this particular scenario, the both inputs are 0, the output is 1. In rest all the cases, the output is 0. And XOR gate. So output is 1 only when the inputs are different. If you look in this particular scenario, 0 0, same inputs, so the output will be 0. In this scenario, 0 1, output is 1 only when inputs are different. 1 0, the output is 1. Again 1 1, the input is same numbers. Okay, in two cases. So the output is 0. Now XNOR gate. So output is 1 when both inputs are same. Output is 1 when the both in this only two possible scenarios 0 0 and 1 1. Rest all the cases the output will be 0. This is about XOR gate. I think this is what about classical gates. You try to mention all those things in the examination. And moving on to quantum gates. It is very important. Please try to utilize this session and listen carefully. So let me start with identity gate. Okay. So identity gate is represented as 1 0 and 0 1. And you already know the column vectors. Ket 0 is equal to 1 0 and ket 1 is equal to 0 1. Right? If you apply identity gate with ket 0, you'll be getting ket 0 at the end of the result. If in the same way, if you apply had identity gate with ket 1, again you'll be getting the same output ket 1, right? So what is the thing you need to learn from this operation? So if you identity gate does nothing to our quantum state, that is what you need to learn from this identity gate. Okay. Now moving on to the most important gates, these are the single qubit gates. Okay. Pauli X gate, Pauli Y gate, Pauli Z gate, Pauli Hadamard gate, phase gate. This all are comes under single qubit gates. Okay. So the X gate flips the qubit, ket 0 becomes ket 1 and ket 1 becomes ket 0. How? So the mathematical representation of Pauli X gate looks like this. Ket 0, that is nothing but 0 1 1 0. You already know the matrix representations or column vectors of ket 0 and ket 1. If you have try to apply x with ket 0, then you will be end up getting 0 1. That is what the definition gives. If you apply X gate with ket 0, you'll be end up getting ket 1. Same way, if you apply it with ket 1, you'll be end up getting ket 0. That is the difference. So, whereas in identity gate, you are getting the same output. But whereas here, the Pauli X gate, the principle of Pauli X gate does is nothing but it flips the target. Now, moving on to another qubit gate, Pauli Y gate. So, these are the gate represented using Bloch sphere. So that is also there in our syllabus, Bloch sphere. So if it is rotating, Bloch sphere is nothing but 3D sphere. If in the 3D sphere, if it is the qubit is rotating along x-axis, there comes Pauli X gate. If it is rotating around y-axis, there comes Pauli Y gate. If it is rotating around z-axis, if there comes Pauli Z gate. So these are all came from Bloch sphere. So if you look in this particular scenario, what does this Pauli Y gate do? So y is equal to 0 minus I. I is nothing but imaginary. That is what the importance of complex numbers in quantum. So if you do it, then you will be having phase. I we call it as phase. So if you do it with ket 0, you will be end up getting it, the qubit will be flipping and it is adding phase. So now if you look with ket 1, you will be end up getting 0 again. The flipping is happening, but what is happening is particular scenario, you are ended up getting minus I, we call it as phase. Okay, that is what happens in Pauli Y gate. It flips and also adds space to the terms. Okay, now moving on to Pauli Z gate. This is the mathematical representation of Pauli Z gate. If you do the mathematics operation of z of ket 0, then nothing is happening. It is returning as ket 0. But if you do it with ket 1, you are also getting ket 1, but you will be end up getting minus. That minus we call it as phase. So if you look here, it rotates the state 180 degree around z axis on the Bloch sphere. From there, this Pauli Z gate has been represented. Okay, that is what you need to remember. Now, moving on to Hadamard gate. So, Hadamard gate creates the superposition. Why we call it as superposition? I already mentioned. If you find the probabilities, you will be getting equal probabilities, 1 by 2, 1 by 2, right? That is why we call it as superposition. So, the matrix representation of Hadamard gate, it looks like this: 1 by root 2 of 1, 1, 1 minus 1. If you do it with ket 0, you'll be end up getting this equation, right? 1 by root 2 ket 0 plus ket 1. If you do it with ket 1, you'll be getting minus. So that is the small difference. Here the change will happen. Here you will be reflecting minus and here it is reflecting plus. That is the only small change is happening in Hadamard gate. Okay. So applying H2 ket 1 creates superposition but with negative phase. That is what I mentioned. Okay. Now moving on to another gate, phase gate. That is nothing but S gate. So this is the mathematical representation of S gate. So if you do it with ket 0, you'll be end up getting ket 0. If you add with ket 0 S gate, then you'll be end up getting ket 0. But if you do it for ket 1, you'll be end up getting phase I. Okay, that is what the operation of phase gate. Now moving on to T gate. This is also called as pi by 8. Sorry, pi by 8 gate. And this S gate we call it as pi by 4 gate. Whereas T gate we call it as pi by 8 gate. So this here I think I forgot to mention pi by 8. So the gate also known as pi by 8 gate. Okay. So this is how the representation looks like. It is represented as T. So 1 0 0 e power I pi by 4. So if you do the matrix multiplication, then you will be end up getting again ket 0. But when you are applying it for ket 1, you will be getting e power I pi by 4. That is nothing but phase. Okay. introducing a smaller phase shift to S gate. That is what happens when you apply T gate. Okay. Now, this is until this we call them as single qubit gates. Now we here comes multiple qubit gates. Okay. So if you look here in this particular scenario, C naught gate. This is the mathematical representation of C naught. So if you look here, 1 1 diagonally till here it is okay. Then rest is 0. And again if you look here, 1 1 diagonally. This is how you need to remember shortcut remember method. Okay. So one is two ones are like this and two ones are like this. Then rest all the elements are 0 0 0. 4 by 4 matrix. Okay. I think C naught gate I will explain here the diagram. So that is control. This is target. So C naught is for multiple qubit gates because we require two qubits, right? 0, for example, 0, 0, 0, 0. So this is two qubit system. Okay, here it will be there. I'm again and again saying this is a worst scenario. Some are even not able to draw this circuit also for C naught. Okay. So I think this is the mathematical representation. This is all not required. You people already know. Okay. Now moving on to another gate, controlled Z gate. Same as C naught gate, one more multiple qubit gate it is there. Controlled Z gate. So which is nothing but it adds phase flip. Okay, only for one. Okay, in this only in this particular row, it adds phase. So this CZ gate you easily can remember. So all diagonal elements are 1. Respect at last element it is -1. Okay, that is what C naught gate do. So it only adds phase when you apply C naught CZ of 1 1. Let us say in this particular scenario you're having one element, right? So that is why it is adding phase. For example, it is 0 0, nothing. If it is 0 1, first qubit is 0, that is why no phase. If it is 1 0, nothing. If it is 1 1, if the two qubits are 1 1, then it adds phase. That is what the operation of CZ gate. I think this is very easy to remember, right? Now moving on to another type, swap gate. What is swap gate? So before going on to all these theoretical things, I will explain here itself. So if it is 0 0, the output state will be also 0 0. If it is 0 1, if in the input, if it is 1 comes, then it will swap it. If it is 1 0, again it is swapping 0 1. If it is 1 1, then it will also swap, but the thing is the result will be same, right? That is what about the swap gate. Okay. Now moving on to another multiple qubit gate, Toffoli gate. So Toffoli gate, you please write at least one point. That is nothing but which is also called as controlled NOT gate, C naught. In this particular thing, in this Toffoli gate, we'll be having two controls, one control and one target. I think better I will explain. So you'll be having two controls. This is 3 qubit gate, okay? Two controls and one target. One target. I am not able to draw. So two controls. The dot symbol represents controls and the plus symbol represents target, right? So what does this do? It acts on 3 qubits, two controls and one target. It flips the target qubit when only the qubits are 1. Okay. Only if qubits are 1, the target will be flipping. Rest all the cases, the target remains same. Okay, that is what about Toffoli gate. I think this is clear. If it is clear, let me know in the comment section. Who is that movie's Kingdom? if it is clear, let me know in the comment section. This is about single qubit gates, multiple qubit gates. I think the question is there in your mid too, but most of you people are not aware about single qubit gates also. If it is clear, let me know. I will proceed. So can you please let me know your names? Dynamo Gamers, please let me know your name. And even the movies Kingdom also, I want to know some name of them. So I think if any question comes regarding classical gates versus quantum gates, are you able to write all those things? Yes or no? Let me know. Give me the clarification, and I will proceed for the next PPT. I think we are investing much time in this comment section only. I don't know why you people are not responding still. S- Now, I think we finished. Uh, I need to mention physics also we finished. I need to mention about biology, and you already know what we need to write: bits versus qubits, classical versus quantum information. Better I will finish this classical versus quantum information. So this is about if any question comes regarding what is quantum computing and try to mention about uh, bits versus qubit, then please write all those things. So classical computers process information as bits, 0 and 1, whereas quantum computer use qubits. They can be either 0 or 1, even both at once. That we call it as superposition. That is what the fundamental that we learned today, right? So this special ability gives quantum computers their amazing powers, because you already know we can solve to, in 2 power n, 2 power n exponential power, right? So classical bit is like a switch, whether it will be having only on and off. Whereas quantum bit like spinning coin, it will having two states at a time. If it is spinning in the air, we will be having two states, both heads and tails, right? Now bits are represented using 0 and 1. But whereas quantum is represented using this particular equation, alpha ket 0 plus beta ket 1, where mod alpha square plus beta square is equal to 1. So here the qubit can exist in combination of 0 and 1, that we call it as superposition until we measure it. If we measure it, it will collapse to one state that we measure, that is nothing but the measured state. Okay. So moving on to the comparison table. So classical information is processed using bits, whereas quantum information is processed using qubits. That is nothing but either 0, 1, or both we call it as superposition. So in classical, that it will be having definite state. Definite is nothing but deterministic or fixed state. But whereas in quantum, we'll be having probabilistic state. So the classical information is processed by or represented by voltage or charge. But whereas here they will be represented by photons, electrons, atom spin, etc., etc. I think atom spin, spin up, spin down. Okay, that is how we will be representing. If it is spinning up, we will be representing it as ket 0. If it is spinning down, we are representing it as ket 1. So here the processing power is nothing but we will be having only one calculation at a time. But whereas in this particular quantum, we will be having 2 power n possibilities. That is why quantum is so powerful, right? Now moving on to another thing. So the output is deterministic. Deterministic is nothing but the future is fixed, right? But here where the output will be completely probabilistic, that you need to write. That is the major difference between classical and quantum. Okay. Data stored as zeros and ones, but here data is stored as wave amplitudes. Communication signals uses, they will be using electrical signal, whereas here we'll be using entangled photons for communication. It can be hacked. The classical information can be hacked, but whereas here it is secure due to quantum key distribution, right? In classical, there will be no entanglement, but whereas here there will be entanglement which links the qubits over distance. So error correction is very simple in classical, but here in quantum error correction is very complex because you need to identify everything. So the so we'll be having ancilla. I think this I think I mentioned in the class. We'll be having ancilla, right? Ancilla. So ancilla is nothing but helper qubit to predict the actual qubits, but whereas syndrome, we call it as error. If error comes, that we call it as syndrome. To identify the error, we will be having helper qubit that we call in quantum terms ancilla, right? There will be no interference in classical systems, but whereas here interference enhances computation. Easy scaling of bits, but qubits are very hard to maintain because of decoherence. Decoherence is nothing but disturbance from the environment. Okay, right. So these bits are used in normal computers, but whereas in quantum computers we'll be using qubits already. Will some companies IBM and Q has even Google Sycamore using these qubits. Okay, I think this is not required. These are the 15 differences you need to mention if any question comes regarding classical versus quantum operations, logical operations, or bits versus qubit. Operations nothing but we'll be having only one operation at a time in classical. In quantum, we'll be having two power in operations. That is, but try to mention all those 15 differences if any question comes regarding this topic, classical versus quantum logical operations. Even bits versus qubit, it is clear, right? If it is clear, let me know in the comment section. Remembering all these types are little difficult. So what I say is nothing but try to remember some easy ones. For example, I can say that you should write at least poly X gate, poly Y gate, poly Z gate, and even Hadamard gate is also easy. At least you try to write compulsory, at least not at least compulsory, you write these four types. Then if you are not able to remember phase gate, S gate, so can you can easily skip those things, and better you try to write at least two types in multiple qubit gates. So my personal suggestion is nothing but control Z gate and C not gate as well as TOEFL gate. You try to draw the diagram for control C not gate, one control and one target, whereas controlled not gate, that is nothing but TOEFL gate, we will be having two controls and one target. So try to write those diagram and try to write some keywords. Better write. I don't want you to write all those mathematical representation. I know that is tough to remember, but the thing is, at least write what C naught does. If control is zero, target will be zero. Nothing happens to the target. If control is one, target flips. That is some operations. Okay, try to mention it. Is that okay, Shasi? Let me know in the comment section. I will proceed for the next topic. I think we are we just left uh, biology left behind. I think we'll finish it. Okay. So importance of biology, the role of biology in quantum computing. Why we required quantum computing in biology? So, for example, let us think about one scenario about corona. Let's think about corona. During corona, it is extremely hard to find the medicine or some other vaccine to for the people who suffered from it, right? So, which is nothing but classical computers are not that powerful to identify what is the cause of corona and what is the medicine for corona. So for that we require powerful computing. So that is why quantum computers, which is nothing but quantum computer, have the ability to solve a problem in exponential way. So that is why it can solve some biological problems very easy way. For example, corona. We can identify why it is happening, in which area it is affecting, or how we can get some immunity booster some from by some uh, proteins, etc., etc. We can test them easily. But whereas in classical system, it is very tough to generate all the data. That is why we require quantum computing in biology. Okay. Now, genomics. Already, genomics is nothing but genes, study of DNA. So, quantum computing helps in sequence in matching DNA. For example, recently you people already know some bus accidents, etc., etc., has happened, right? Their bodies given to their I think you are aware of that, right? It was very late. Why? Because classical computers are very or classical systems are very hard to figure out whether which DNA matches and what are the molecules that are involved. So that is why we require quantum computing. Okay, in genes alignment, in mutation prediction, future prediction, we require high computing. That is why quantum computers help us to solve all those things using these fundamental. Okay, so the example I have given here, please look. Finding a specific genes pattern in 3 billion letter long DNA sequence. 3 billion letter. Okay. So think of how big number it is. So it is very hard, right? It is very hard to figure out, right? So it may take classical hours to solve for hours or even days or even years. But whereas a quantum computers, like already we know Grover's algorithm, Grover's can do it much faster than existing classical methods. Okay. Now identifying proteomics. That is, proteomics is nothing but the study of proteins. So proteins fold in complicated 3D shapes. It is very hard to uh, uh, process 3D shapes in classical systems. Okay, but quantum computers can simulate the protein folding 3D shapes very easily. Okay, by using these protein folding and molecular energies as well as drug protein binding, we can easily identify, or we can easily identify what is the drawback. Okay, now for example, I given one example here. Quantum computers can help design drugs faster. For example, which will be useful for cancer, COVID, and diabetes, etc., etc. During COVID, it was very hard, right, to find the vaccine for us, right? So another thing is nothing but central dogma of biology. So central dogma of biology is nothing but the mix of DNA, RNA, and as well as protein. Okay. So this is the central rule of biology. So DNA is nothing but which stores the information of genetics. So I will give one clear example with some uh, uh, real life example. Think of it is like a big recipe book. Okay, including all these three. Think of it is like a recipe book. So the RNA is nothing but the transcription of that book. Okay, the cell makes a copy of specific recipe, genes recipe. It will give the transcript for genes recipe. This copy is called RNA. Okay, like photocopying one page of the recipe book. Just think. Okay, now moving on to the third thing is nothing but protein. So this cell uses the RNA copy to build proteins. So RNA will have one copy of DNA, and DNA from this copy protein will be used to make to build some proteins in our body. So proteins do almost all the work in our body. Okay. So DNA is nothing but a recipe book. RNA is nothing but a photocopy of recipe. And protein is nothing but final dish to cook. That is what we require for our body. These simulations are very tough in classical computers. But whereas in quantum computers, it is very easy. We can find which is the protein or which is the thing we require for our body to get over from all those diseases, cancer, covid, diabetes, etc., etc. It won't take many days or many years to solve all those things if the quantum computer comes. It may require just less in, I can say, it requires only just in seconds or minutes. Okay. I think this is about quantum biology, importance of biology in quantum computing. Sorry. So if it is clear, let me know. It is completely theoretical. I think it is not much uh, to elaborate. If it is clear, then we'll move forward. So we'll be having only three types: genomics, proteomics, and central dogma. And central dogma will be there in unit 2 also. If you look in this particular scenario, again the same thing has been here. So background biology, basic concepts of genomics and proteomics and central dogma. Again, the same thing is repeated. If you are familiar with this, then we'll proceed for the next topic. Is that okay? Let me know in the comment section. Yes, please. I will proceed. Almost we have finished unit 2 also. Make it fast. I will finish. I want to wind up the session by 7:30. I don't want you people be hectic. Okay, thank you. So now moving on to, I think quantum information versus classical information is done. Basic logical gates is also done. Gates, quantum gates is also done. And types of qubits. This is the thing you need to study as of now. Fundamental principles of quantum done. Role of mathematics in quantum is also done. Transition from classical to quantum is also done. So now moving on to the most important topic, types of qubits. This is the part of unit 3. So what is qubit? Moving on to, before going on to the types of qubits, what is qubit? So a qubit is nothing but a quantum bit, right? Which is the smallest unit of quantum information. So classical bit will be 0 or 1, but whereas a qubit can exist in superposition, it can be represented as this particular state, ket psi is equal to alpha ket 0 plus beta ket 1, right? Where mod alpha square plus mod beta square should satisfy the equation, this normalization condition 1. Now we are having different physical qubits. So some are man-made, some are nature-made, etc., etc., right? So one is spin qubit, another one is trapped atoms and ions, and the third one is photonic qubits. In photonic qubits, we'll be having three types: polarization qubit, time qubit, and path qubit. And the fourth one is nothing but superconducting circuits. And the fifth one is nothing but quantum dots. And the last one is nothing but nitrogen vacancy centers in diamond. Okay. Before going on to the types of qubit, I wanted to discuss about the first qubit, that is nothing but spin qubit. So spin qubit uses the angular momentum. These terms should be there in your exam. Please highlight these particular terms. It will boost. So the electrons will be having only two types of spins. Either it is upward or downward. Okay. So now, if the electron is spinning upward, how can I know the quantum state? If it is upward, scientists had decided this as ket 0. If it is downward spin of the electron, we'll be having it as ket 1. Just think of a ball. You'll be having only two spins, top spin and down spin, the same as electrons. If it is the ball is spinning upward, we call it as ket 0. If the ball is spinning downward, we call it as ket 1. So we'll be using magnetic or microwave fields. Okay, if the electrons is having only upward spin, I am using these microwave fields to manipulate spin orientation. If it is upward, I am sending these microwave fields to this particular electron spin, and I am making it move to downward. This we call it as manipulate the spin orientation. Okay, the terminology is we call it as we are manipulating the spin orientation by using magnetic or microwave fields. The advantage of spin qubit is nothing but simple physical concept which is very small in size, and it is compatible for semiconductor materials, okay, which can be easily integrated. Okay, disadvantage is nothing but which is sensitive to magnetic noise. So if any other noise or decoherence happens, it will collapse. It requires cryogenic cleaning. Cryogenic cleaning is nothing but minus 273, minus 273. I'm again saying not positive 273. Just think of how much cool it requires. Minus 273 degrees Celsius it is required for spin qubit. Okay. So as I already said, if it is spinning up, get 0. If it is spinning down, get 1. Right. So now moving on to another qubit, trapped atoms and ions. Name itself has trap. Okay. Before going on to this, I want to explain here. So initially, the electron or atom will be at low energy state. What I am doing is nothing but I am trapping this electron which is at 0 state by sending magnetic fields. I am not able to write, so I will write MF, magnetic fields or lasers L, or microwaves MW, magnetic fields or lasers or microwaves. I am using them to trap this electron to and making it to move to high energy state. Why I am doing all those things? The qubit should have two states, right? 0 and 1. Right. So if it is only if the atom is only having only one state, it becomes classical atom. So what I am doing is nothing but to make it to behave as quantum bit. I am doing all this trap by sending microwaves or micro magnetic fields or lasers onto these qubit, and I am making it to move to high energy state. That is nothing but 1. That is what about trapped atoms and ions, and I have given the definitions here. So atoms or ions trapped using magnetic fields, electromagnetic fields. So initially they will be at 0. What I am doing is nothing but I am trapping them and making it to move to excited state. That is nothing but ket 1. So please look here, lasers, microwaves. Okay, these are the things we'll be using to trap the atom. So advantage of these trapped atoms and ions is nothing but they can stay for long coherence time, and the information will be extremely accurate. Okay, and it is ideal for research and precise quantum logic. Okay, but this disadvantage is nothing but we'll be having slow operations. Large experimental setups are required, and we are having limited scalability as of now. And moving on to time in. Before moving on to time in, I want to discuss about photon qubit. So photon can travel in three ways. Okay, one is vertical, one is horizontal, another one is diagonal, and the last one is anti-diagonal. So these many ways the photon can travel. Okay, so how I will represent time for that photon? Okay, I know only the paths. So how to decide the time? For example, I am having a beam splitter. This is called beam splitters. I am using beam splitter BS, and what I am doing is nothing but I am sending a photon to beam splitter, and if some photon comes by diverging the beam splitter, if a photon comes first, I am marking it as early arrival and I am measuring the basis as ket 0. If the photon is coming late, the same from the same beam splitter, if the photon is coming late, then I am marking it as ket 1. Okay. The main advantage, so that is what I mentioned. We will be using beam splitters and delay lines. Okay. To create, to know whether the photon is coming early or not. Okay. That is the main advantage. Okay. So which is excellent for stability for over long everywhere now as of now many countries and many quantum computers everything entanglement will be using all they will be using photonic qubits to transfer energy or to transfer information. Everything photonic qubits has been using as of now. So it is perfect for fiber based quantum key distribution. In quantum key distribution also China's Messier satellites has performed. They will be using, they have been used photon qubits. Okay. So it requires fast detectors. Okay. To know whether this is working properly or not, we require fast detectors, and precise time synchronization is must to identify all those things. That is the disadvantage. Okay. Now, for the same qubit, we are having path qubit. So again, in the path qubit also, we need to know the path of the photon. Again, we are using beam splitters. Again, we are making it to travel through the beam splitter. If the photon is coming hit on the beam splitter and it is traveling top path, top for example, and some are coming bottom, let's say, I'm denoting it as B and T. If the photon is traveling top, then I measuring it as ket 0. If the photon is hitting the beam splitter and traveling down, I am mentioning it as ket 1. Okay, that is what about the path qubit. So the main advantage is nothing but it integrates easily into photonic chips and which has high control precision. But disadvantage, the main thing you need to remember, it requires stable alignment and suffers from phase drift. Okay, I think this is what I mentioned about the diagram. This is about the diagram. Okay, top path and bottom path. So one more thing I forgot to mention, polarization qubit. So what is polarization qubit? Polarization use electromagnetic fields. So this is how polarization qubit travels. If it is along vertical, it will travel as waves. If it is along with horizontal, it travel at waves. If it is along with diagonal, it travel as waves. This is how photonic polarization qubit travels. So nothing much. How these photons are traveling on this direction, that is what mentions in polarization qubit, horizontal, vertical, and this we call it as a diagonal. Even in anti-diagonal also it will travel as in in the same way. Okay. Now moving on to the most important qubit, superconducting qubit. So before going on to that, I want to explain you pictorially, and this is about the diagram of superconducting qubit. We are having a circuit with low resistance. So just think of how these two directions came here. Two directions are there, right? So how can a low resistance circuit can have two directions? I'm making it as, if it is clockwise rotation, I'm making it as 0, and if it is anti-clockwise rotation, I'm making it as 1. But the thing is how this is traveling, or this circuit having two directions at a time. Any idea? Any idea? Let me know how it is happening. Any idea? Yes, no, please let me know in the comment section. Srikant or Sesi or someone, please respond. Jaya. Are you having any idea how this we are having two directions in this circuit? Anyone please respond? Question is nothing but Rohit. The question is we are having, okay, let me clear it out. We are having a circuit with low resistance. Okay, circuit should only have one direction, right? So, but in this particular diagram, I mentioned two ways, clockwise and anti-clockwise. How? How that is happening? That is what my question. In superconducting circuit or a qubit is required two operations at a time or two states at a time. That is why I have given this example, I have given this picture. But the thing is how it is created, clockwise and as well as anti-clockwise for the same circuit. That should be, it should be like either clockwise either or either anti-clockwise, right? But how? That is what my question. Rohit? No. Srikanth said no, and someone 4161 also said no. Probably sending no. Probably sending no, no. That is not the answer. Here, so please listen carefully. Here we'll be using Josephson junction. Josephson junction. I'm not able to write junction. So we'll be using Josephson junction. What does Josephson junction do is nothing but it splits the current to flow in two directions. Okay. Now you got my point, right? So here there will be Josephson junction. No, no, no. We'll be using low resistance for superconducting circuit, but it won't make them to travel in two directions. But the thing is, Josephson junction makes it to travel in two directions. So it is clockwise and as well as anti-clockwise. Okay. So I think this is what about superconducting circuits. So what we are doing is nothing but if the current is flowing or if the qubit is flowing through clockwise direction, then we are marking the qubit state as ket 0. If it is the qubit is traveling in anti-clockwise direction, we are marking it as ket 1. If two states at a time, we call it as superposition. That is what about the diagram. And now moving on to the definition. So tiny superconducting loops carry electrical signals without resistance or with at low resistance also we can say. So if the current is traveling clockwise, we call it as ket 0. If it is anti-clockwise, we call it as ket 1. So these current state exists in superposition. We want anything. If we want to represent anything in quantum, we want two states. It is not like I have only 0, I can represent this as in quantum. No, we require two states. Okay. So we'll be using microwave pulses to control transitions between quantum current states. Okay. The main advantage of this superconducting circuit is nothing but we'll be having fast gate operation compared to other qubits, and which is very scalable. We'll be using scalable chip fabrication, and already this has been implemented by IBM as well as Google in their processors. But the main disadvantage that you need to remember is nothing but it requires near absolute zero temperature. That is nothing but 15 millikelvin or minus 273 degrees Celsius. And we require them to stay without any noise. It is also very tough, right? Tough challenge. That is what the disadvantage of superconducting circuits. This is about the circuit. And before going on to this, so this is how quantum dot looks like. What we are doing is nothing but we are having a 3D, for example, just think of like it as a ball, and ball has two layers. One we call it as QD core, another layer we call it as QD shell, and the last layer we call it as protective shell. And what we are doing is nothing but we are making a dot here. Okay, in that particular ball, we are making a dot, and in that dot, we are inserting the spin qubit, which has only two directions, upward or downward, to represent the basis states of quantum, right? So, why what is the reason all those things we need to one need to do? The thing is, it will not have disturbance from the environment because it has the protective shells. So that is why we are making it to happen. Okay, that is what the diagram says. So a quantum dot is a nanoscale semiconductor structure that confines a single electrons. Okay, we can only uh, adopt a single electron in this particular dot. Dot is nothing but a hole. Let's think. Okay, and we are inserting one electron in that particular dot. Okay, if the electron is present, then we call it as ket 0. If the electron is absent or spinning down, we are marking that basis state as ket 1. So for this, we are using voltage gates and microwave pulses, and we are manipulating the electron states. Okay, and advantages, disadvantages is not required for you people for this particular thing. And the last thing is nothing but NV centers. So I think you are aware, right, of how diamond is made. See, carbon lattice, right? This is how carbon lattice will be looking like, right? I think this structure is there in your childhood. I think this is how carbon lattice look like. What is this nitrogen vacancy center? Name itself has nitrogen vacancy center. So what we are doing is nothing but we are erasing this. For example, I am erasing this. I am replacing this. I am replacing this with nitrogen molecule. If you replace a carbon molecule in diamond with nitrogen molecule, the adjacent state will be va- vacant. There will be no element, either nitrogen nor carbon. It will be vacant. In this particular vacancy, we are filling an electron again. Electron again has two directions, spin up and spin down. And we are making it to behave as qubit. That is what about nitrogen vacancy centers. Okay. So if you move on to the diagram or move on to the concept. So a NV center forms a when one carbon atom is in diamond is replaced by nitrogen atom, leaving a vacancy next to it. So which is used for to trap the electron. So which is if it is spinning upward, ket 0, if it is spinning downward, ket 1. So the main advantage of these NV centers is nothing but NV centers in diamond is nothing but it can operate it in room temperature also. Due to the strong lattice, it will be having long coherence times. So excellent for quantum sensing and magnetometry. So but the challenge is nothing but cost point of view and even difficult to produce identical NV centers. That is what okay about the types of qubits. I think basics of linear algebra is covered in unit 2. Probabilities is covered. Background physics, Pauli exclusion principle. I think I need to cover them. And basics of quantum mechanics. You can write all those basics of superposition, entanglement, etc., etc. Or you can write anything, no issues. And we have covered physical implementations of qubit, a quantum bit of information also we have covered. Single qubit gates, multiple qubit gates, designing the quantum circuit, that is nothing but the entanglement circuit. And I need to cover Bell states and the Bloch sphere. So the Bloch sphere is nothing but a 3D sphere. In the 3D sphere, if it is rotating along x-axis, there comes Pauli x gate. If it is rotating along y-axis, there comes the Pauli z gate. If it is rotating z-axis, there comes Pauli z gate. If it is along in between, let's say x and y, that is Hadamard gate. From there, from the Bloch sphere only, this all gates has been derived. Okay. I think almost we have covered Unit 3 and even Unit 2 also we have. Unit 1 completely we have covered. I think is that clear? If yes, I will finish the session. Tomorrow we'll complete syllabus. Today I'm giving some excuse. If tomorrow if same thing happens, I don't even take this revision session also. It is not required. If anyone fails in exam also, I am not the one responsible because from my side I'm giving 200% efforts, but from your side you're not able to join the session also. I have given some extra time for these all those things. I think it is very useless. If it is yes, please let me know. I will wind up the session. Tomorrow I will discuss about Pauli execution principle, superposition, entanglement. So I think already I covered superposition, entanglement, and supersymmetry, density operators, and correlation should be covered, and also measurement should be covered. I will give one. I will solve it one with one example. So please let me know if yes. Let me wind up. Are you there, anyone?